There's a question from GATE 2014 from Chemical Engineering, question number 38. A vapor phase catalytic reaction Q plus R giving S follows radial mechanism where R and S are not adsorbed. Initially, the mixture contains only the reactants in equimolar ratio. The surface reaction step is rate controlling. With constants A and B, the initial rate of reaction minus RO in terms of total pressure PT is given by dash, and the four options are given as here. So this is a question from catalysis part in chemical reaction engineering, and the reference NPTEL lecture can be found in lecture 2, steps in catalytic reaction, adsorption, desorption and reaction, chemical reaction engineering 2 by Professor Sanjay M. Mahajani, Professor Ganesh A. Vishwanathan, Professor A.K. Suresh from Department of Chemical Engineering, IIT Bombay. So here the reaction given to us is in vapor phase, and that is Q plus R giving S. And this follows Eley-Rideal mechanism. And in the question they have mentioned that only Q is getting adsorbed. R and S are not getting adsorbed. So based on this, we'll try to formulate the different steps in the reaction and their corresponding rates according to Langmuir-Henselwood approach. So here Q plus R giving S is our overall reaction, and Q is the only thing that is getting adsorbed. So the adsorption step will be Q plus V reversibly giving QV, where V is the vacant site, vacant active site. Then the reaction step will be QV plus R giving S plus V. Since the product is already in a desorbed state, there is no desorption step. So there are only two steps here. Step number 1, which is the adsorption step, and step number 2, which is the reaction step. So we can write the corresponding rate equations as well. So if we write, rate of adsorption, it will be, let's take it as Ka and K minus A as the rate constants for this adsorption step, and the reaction, let us take it as Kb and K minus B. So for the rate of adsorption, the overall rate of adsorption can be written as Ka into Cq Cv minus K minus A Cqv, and the rate of reaction can be written as Kb Cqv Cr minus K minus B Cs Cb. Now the concentrations of CQ, CR and CS it can be written in terms of their partial pressures as well. So if we write the reaction rates in terms of partial pressure, we can write rate of adsorption as Ka PQ CV minus K minus A CQV, and rate of reaction as Kb PR CQV minus K minus B PS CV. Okay, so let us take this as equation 1 and equation 2. Now, one more equation we can write the total side balance. This will be CT, that is equal to CV, the vacant site concentration, plus CQV, which is the concentration of the adsorbed reactant Q, or the concentration of the activated active sites. So let's take it as equation 3. Now, here it is mentioned that reaction is rate determined. So that means we can take rate of adsorption as 0. So that means Ka PQ CV minus K minus A CQV is equal to 0. So from this we can write the equation in terms of CQV as CQV is equal to Ka by K minus A PQ into CV. Now this Ka by K minus A will give you the equilibrium constant Ka, because Ka is the forward rate constant and the K minus A is the backward reaction rate constant. And the ratio of the forward to the backward reaction rate constant will give you the equilibrium constant capital Ka. So CQV can be written as capital Ka PQ into CV. Now what we can do is we can find the term for CV by using the side balance. So from equation 3, the side balance CT will be CV plus CQV. And we can substitute for CQV as CV plus Ka into PQ CV. So from this, if we rearrange, we can write the term CV separately. So CT will be CV into 1 plus Ka PQ, or CV will be equal to CT by 1 plus Ka PQ. So let's take this as equation 4 and this as equation 5. Now, we will substitute these values for CQV and CV in our rate determining step, which is our reaction rate. So, our reaction is will be the rate determining step. So that will be R overall, and that will be equal to KB PR CQV minus K minus B PS CV. So substituting for CQV and CV, so R overall will be equal to KB PR CQV minus K minus B PS into CV, and that we substitute for CQV and CV, will get KB PR CQV is Ka PQ and CV minus K minus B PS into CV, and CV will be CT by 1 plus Ka into PQ. Now we substitute this CV here as well. So we'll have KB PR Ka PQ into CV, that is CT by 1 plus Ka PQ minus K minus B into PS Ct by 1 plus Ka PQ. So we can take these two terms out. So Ct by 1 plus Ka PQ into Kb into Ka PR PQ minus K minus B to PS. So this will be our overall reaction rate. Now they said that initially only the feedstocks are present or the reactants are present. So initially only Q and R are present. That means S is 0 initially. So if we write overall reaction rate at initial stages R 0, then here PS will be equal to 0. So in our overall reaction rate at initial stages at T equal to 0, this PS term will get cancelled. So our new reaction rate at the initial time T equal to 0 will become minus R0 equal to KB, KA, PR, PQ, CT by 1 plus KA, PQ. Now if we take KB into KA to CT as a constant A and KA as B, we'll get this initial rate as minus R0 is equal to A into PR PQ by 1 plus B PQ. Okay. So now, since they have given in the question that R and Q are equimolar in the system. So that means we can take PR equal to PQ and that will be equal to the pressure PT. So what we can do is we can substitute PT in terms of PR and PQ and we'll get our initial rate minus R0 as A into PR into PQ, which is PT into PT, that is PT square by 1 plus B into PQ and PQ will be PT, so B into PT. So our initial rate equation will become minus R0 equal to A into PT square by 1 plus B into PT. Now this is our required initial rate and this is the same as the option C given in the question. So our required answer here is option C, minus R0 equal to A into PT square by 1 plus B into PT. So that is our initial rate of reaction in terms of total pressure for this given question.